All right, for our second video, I'm going to be talking about the losses in a boost converter. So on our last video, I don't know if you have seen it. If you have seen it, great. If not, please go back and watch the last video. We went over how to derive the component values for our boost converter. So this was our inductor and capacitor, just the size of them. And I showed that there's the sheet here. I think I forgot to show exactly where the sheet was. So if you are in UBC Solar, you can go to UBC Solar under Brightside 2025, under the elect folder, pass folder, projects, and custom MPPT, and boost converter. It's right in here. So this is where we derive these equations that I've put here. And you can see that when we change certain things, the values of these components will actually change as well. Which is super nice if we're designing multiple converters or if we want to change certain parameters and see what's going to happen. And what we're working towards in this video is this efficiency number. So we've assumed 98%. It's not going to be 98%. It's going to be something different. And how we derive some of these things are through some assumptions and some component selections that we make here. The first one we're going to be doing is the MOSFET, and then we'll work on the diode, the inductor, and the capacitor. Those will be our major forms of losses in the converter. And then that'll give us a total power loss. And then based on the total amount of power we're pushing through it, that can get us our efficiency, which will be this, just our 1 minus our total power losses divided by our output power. So we kind of have an idea of what we're working towards. Let's start with the MOSFET. So a MOSFET is a switch. Some people disagree with me, but I'll say it's a switch for now. When you put a signal here where you start from 0 and then you increase and put it to some 1 is what I'm indicating here. When you put a signal on the gate, that is going to close from the drain to the source and allow current to flow. Different types of MOSFETs have different behaviors. Some you need to start with this and then drop it to 0 in order to close it. But we're just going to start with the most common, which is when you apply a signal to the gate, it'll close this. So what happens when you try and close this as a switch? We're going to start with when you try and, close this as a switch. So you're applying some signal to here. You want to turn the switch on and close it. So that's our VGS here. So our VGS is the voltage here. That's the signal that you need to apply to turn the switch on. So let's draw that really quick here. So we're saying at some time here, we are going to turn the switch on. And what happens? Well, our voltage here, we would love for this to drop instantly. This needs to go from whatever the VDS is down to 0. Because that means a short circuit. And that means the current will also need to go from 0 up to some value and stay there constantly. If that happened, we'd have 0 power losses, but this is about power losses, so obviously that's not going to happen. The reality is, we'll start with the current here. The current initially is 0, and then when we try and close this switch, the current takes time to get up. And we see that the current will actually, when we turn the switch on, it's going to ramp up from that time up until the second time. Straight line. So it's a straight line ramp up from that first initial time we turn the switch off to some middle time we call here. This is our kind of on time, or like open time. This total amount would be, this is 1/2 of that. So half the time it takes, the current is going to ramp up. And we see here that the voltage actually in this time stays constant. So as the current is increasing up, the voltage here actually stays constant, meaning you need to maintain that voltage to ramp the current all the way up, and then that voltage can start to come down. And again, that voltage does not come down instantaneously. That voltage takes some time to come down, and it's going to ramp down linearly as well between this sort of middle time here and our total end. And during this time, the current has maintained its constant value, which is its full current. And then the voltage will drop to some very, very low value, which will approximate to 0. So here we go. You can kind of see where the power losses might come from. Well, anytime where we have the voltage positive and the current positive, we're going to have some power that's being dissipated across the switch. So that's every time in here, there's going to be some power loss. And we're just multiplying these two to get the power losses, which will look exactly like that. So that's what it looks like, and we can kind of walk through what the values are here. So this top value is actually just going to be the voltage here and the current here. This current here is just our current on, and this voltage here is just our voltage when it's off. So we can call this like V off. Drawing with the mouse doesn't agree with me, but this is our current on and our power max. So this is our instantaneous power, but what we are more interested in is over the lifetime of the converter operating, what actually is the power, because this is operating at a very high frequency but a very small period here. Like the actual times that this is happening make up only a very, very, very tiny percentage of what the total timeline of the converter operating is. But these power losses do end up being significant, and we can calculate exactly what they are by looking at actually the integral of this, which is just energy. So we can look at the total energy, and then we can just multiply that by the number of times that that's happening per second. So what that's going to look like, basically, what I'm saying is that the power for the like switching on, because we switch off as well, right? So the power to switch on is just going to be, in this case, we're looking at the energy. So energy times the switching frequency. So this is basically how many times is this happening? How many times are we turning it on? And then that's the energy. And so this is going to give us our total power losses. So let's take this and we'll go with the power on. I'll just imply the switching is going to be the energy here is the integral. So it's the area under the curve is 1/2 times, in this case, the height is going to be I on times V off. So I on times V off times our switching frequency. Times our base here, which is this time here. And we'll just call this T switch. That is our power basically in the instantaneous time where you turn it on. So this is our area under that curve, which is the energy, and our switching frequency. So we can go back to our sheet here and we can look at, So let's look at the other section here, which is turning it off. So when we're turning it off, we have some signal where we're turning it on and we're dropping to 0. So let's draw that here. And I'll run more quickly through this. So when we currently have it on, we're pushing current through. We're trying to open it and let no current through. So when we have current that's being pushed through, in this case, we see it's the voltage that first has to ramp up. So the voltage ramps up, then stays open. And the current is the one that lags and drops off after. That gives us our same sort of triangle here. Doop, doop. With the same values here. So in this case, it's our I on times our V off. So exact same principle as before. We're just looking at what's happening. In this case, it's the current that drops off after. The physics of this, again, not super important, but this is kind of where the formula comes from. And we have a same sort of thing here where we're looking at the energy times the switching frequency. So the area under the curve is going to be the exact same as long as this sort of time is the same, which it is, or we can approximate it to be about the same. So we have 1/2 times I on times V off. It's exact same. 1/2 I on. So this is like our P off. 1/2 I on V off. And T switching. That's our base. So 1/2 height base times our switching frequency. So then we get our total power is going to be P on plus P off. So basically, in case it isn't clear here, when we have a waveform into a switch, this is one period. And in one period, you have one time where you switch on and one time where you switch off. And that's what gets us this, where you have the power losses from the on and the power losses from the off. So this is going to end up being, and we can see it's 1/2 times this plus 1/2 times this. They end up being the same thing. So multiply them by 2, and we get I on times V off times T switching times the frequency. So just I on V off T switching times frequency that you're switching it at. Brings us all the way to here. In times V out. So yeah, this basically means In is going to be the current that is going through the switch at the moment where you're switching. V out is the voltage at the moment where you're switching. T rise plus T fall. So we switched it into a rise time here and a fall time here. I've kind of showed those both as time switching. Then we have times frequency that we're switching, which is this number here. So that's where this formula came from, and that is the switching losses in a MOSFET. And we can see that these are going to scale. I mean, of course, higher currents, higher voltages are going to lead to more power losses. That's normal. But the thing we're really worried about here is when we're selecting something to reduce that is the time. How long is it going to take for you to open and close the switch when you send that signal? And if it takes longer, you're going to have more power losses. The thing that we can change is the switching frequency. So when we adjust our switching frequency assumption here, the lower it is, the less power losses we have. If we half the switching frequency, we half the power losses. Now, other things will have problems. Our components will have to be bigger. We'll have more power losses in those. So there's a balance. But generally, this is why we want to run lower switching frequencies for more efficient boost converters. So that is the switching losses in a MOSFET. But we have kind of two losses that we want to look at in a MOSFET. The first one is the switching one. And then the second one is the RDS on losses, or I call them the on losses here. So this is basically the amount of energy that it takes to maintain that switch to be closed. And the reason that it takes energy is because the switch is not an exact short circuit. It has some resistance. So that's this RDS, we call it. So basically just the resistance between the D and S, so RDS, the drain and source. When we push current through that, it's going to have a power loss. So that's really all that is. I don't want to talk too much about it. It's literally just our I squared R losses, and they're only being incurred at a portion of the time. So if we look at a cycle, a 50% duty cycle, assume that's 50%, or 40%, sorry. So 40% is what our duty cycle is here. We're only incurring these losses when the switch is on. Our duty cycle is how often is the switch on as a percentage. So our duty cycle being 40% means that our switch is on for 40% of our total time. And since we're only incurring these losses between RDS, that's the only losses we're incurring are the time where it's on. So our total power losses are going to be whatever our power losses are in this time times 40%, and that's going to get our total power losses for like the entire time. So that's why we multiply it by the D here. We're just kind of isolating that section. So we only have a portion of those losses because we're not incurring them all the time. And so you might say, well, what about these off? This is just a pretty simple thing. It's basically saying in that other time, we're not exactly an open circuit. There's a leakage current. So we take our voltage that we're at and we take our leakage current, which is usually some very small number. And we multiply that by 1 minus D to get the other section. And we can see that these are very small compared to our on losses very small compared to our on losses or our switching losses. But that gets us our total losses on the MOSFET. And you can kind of see the numbers that we'll need here. We'll need some leakage current to get our off. We'll need here, we need our RDS for our MOSFET. And when switching, we need our rise time and our fall time. So those are kind of the things that we're going to be looking for in our MOSFET. We're going to be looking for a smaller rise and fall time. We want to be operating with a lower RDS, and we want to be looking for small leakage currents. And the small leakage currents is not nearly as important as the other two. So the biggest ones we're looking at are our RDS and our rise and fall time. So we can see that our next section here is going to be on the diode. So our diode, the first one is our forward, jump down here. So first one is our sort of on-time losses, and these are going to make up the majority. So the other stuff I'll briefly mention, but I just want to talk about the basics, which is you have a diode. What does it do? Well, you have a voltage drop across it, usually around like 0.7 volts-ish on power diodes. And when you put a current through that, it's going to cause that voltage drop. And then when you try and put a current back, nothing happens. So what are the power losses going to be? Well, the power losses are just going to be the forward voltage. That's that sort of like 0.7 if we have, times whatever current we're taking through it. So I on, let's call this V forward times I on. There you go. That's our power losses in the diode. V forward times our current. And this is only actually going to be occurred when the converter is actually turned on. So if we remember, a converter is going to look like this. Sorry, our converter waveform, where this is, in our case, 40%, and that's our duty cycle. So our duty cycle is 40%. That is for the switch. So here is our boost converter. We have our inductor, our MOSFET. I'm just going to draw as a switch there. This is our source. And our diode. And this is our output voltage here. So when our switch is closed, the diode is going to be complemented. So when our switch is closed, then that means the diode is going to be open. So the diode is going to be open during this phase, and it's going to be closed in the other phase. So the diode is going to be closed here. So our power losses are actually going to be VF times I on. That's our total power. We're going to multiply by 1 minus our duty cycle. So that's just because this is going to be 1 minus 0.4 is 0.6. So if that's not clear there, and I forgot to do that here, so let's just quickly pop that in. 1 minus our duty cycle. Our off time is going to be the same sort of thing. This is basically just the fact that we want it to be an open circuit when we try and push current back through this way. But it's not going to be exactly that. Our diode curve is going to, our classic diode curve where we ramp up like this, and then here is 0. Well, in fact, there's actually a very, 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 very small leakage current here before it drops off. So when we try and push current through here, there's going to be some that gets through. And we can look at that as basically the voltage that it's protecting against times our leakage current, which we can just get from the diode itself. That's going to be on our on cycle, so 40% of the time. That gives us these losses here. A similar thing, we're separating into two different sections where we have the on time and the off time, but it's just going to be inverted in this case because the diode is complemented to the MOSFET. So now let's talk about the switching here. I've left this blank for now, and the reason is that it's very small, and a lot of data sheets actually don't have this. So in practicality, I tend to just ignore this. However, for completeness sake, a lot of people will mention this. So when I say switching losses, it's not really switching losses, but it kind of is. So when you have a diode, I'm just going to kind of refer to this standard sheet here because this one's actually pretty good. So when you have a diode, when you're turning it off, so this is just from ST, and they have a really good application note here. This is called calculation of turn-off power losses generated by ultrafast diode. When you have a diode, and here's that sort of same thing where we have that duty cycle here, not on the turn on. So the turn on is when you're having no current put through it and then you're trying to push current through it. But on the turn off, when you're, have current, so down here, this I out, when you have current that's being pushed through it, and then suddenly you turn that off, there's this kind of overshoot thing that happens, and it's exaggerated here. It's actually a very, very small little blip, but the current will drop down to 0. It'll go past 0 and become negative for a little tiny period of time, and then it'll come back up. So think of that as kind of like an overshoot happening. And that's strongly dependent on like the characteristic of the diode and all these different factors. And so you see here, they go into more detail about the different curves at different times, the different speeds and stuff. But the important thing here is this kind of little piece. We can calculate based on, this is the current kind of overshooting here. And we have two things that we tend to see here, which is IRM and our TRR, which allow us to calculate our QRR. So I'll go briefly into that. So we have current, drops off, comes back. This is 0 amps. We have this, which is IRM. We have this, which is TRR. Reverse recovery is what this stands for. So these are reverse recovery losses. Reverse recovery. I am not good at writing on this. So reverse recovery losses. So we have something which is the time. This is basically the time that it's going in that negative. So again, this is when you have a diode and you're pushing current this way. And kind of at that moment where you start to push current, not back, but like you stop pushing current, it gets smaller and smaller. This will then sort of allow current backwards. Draw it as red. So it kind of allows current backwards for a second. That is this, what we're talking about here. So current's dropping off, and then suddenly it sort of like overshoots, and you have this actually represents your losses. So the integral of a current on a time graph is Q. So that's where we get this QRR, charge, sorry. And QRR is just going to be the integral. So it's just going to be 1/2, same sort of thing, just a triangle. Zoom in a little bit. Times our time, TRR, times our IRM. And well, we want to go from Q to something more useful, which is power. So to get our power, we want to take the Q. So QRR times our forward voltage, or sorry, our reverse voltage. So this is that voltage that's going to be put across this when we want to turn it off. So when we're turning it off, we want it to be open circuit, and that's because we're preventing a voltage from generating across it. So here, that would be our voltage here, which is our VO, and our ground here, so it's just negative VO, or in this case, VO, because it's negative, negative. So VR times our switching frequency. Same sort of thing as before, so if you don't recognize this is just energy. So volts are just going to be joules per coulomb, and so multiply that by the number of coulombs, we get our joules, so energy, and power is energy times our frequency. And this gets us our total losses. Okay, so our next section we're going to going into here, just following from the sheet, is our inductor losses. Split this up into kind of like our AC and our DC, or some people call it our copper losses, or conduction losses would be our sort of what I'm calling DC. And then our AC losses are our core losses. So this is the effect of when we have an actual core through here and we're generating magnetic field around it. It's going to cause those hysteresis losses that you might be familiar with. The reason I haven't put anything here is because these are hard. These are really hard to calculate. They're often not in data sheets. At some point, I'd like to understand this better, but as I currently understand it, they're hard to calculate. They can be significant, but again, it depends on what you're using and how you're using it. For now, I'm going to leave this blank, and hopefully in the future, I'll fill this out. Let's focus on these DC losses. So this might seem pretty straightforward, and it pretty much is. So we model this as a resistor, and it turns out in data sheets, this is called the DCR. No idea what it stands for. Something resistance, whatever. So that's the value that I put here, our DCR. So here I've found for some specific inductor, it's this value, 20 milliohms. Great. So you might say, well, then you just take I squared R, and that's going to be your losses. The problem is the current through here is not even close to a straight line. So we have some average, and from our previous video, this average is just going to be I in for a boost converter. That is just because the source pushes all of its current through the inductor into the rest of the converter. So that is our average current, and it oscillates up and then down and then back up, with this being sort of one duty cycle. One period. So it's going to go up and down. And that means that we can't just take I squared R, because I is constantly changing, and it's changing by a significant amount. What we need is the RMS current, because if we have the RMS current, we can take IRMS squared times our resistance, which is this, and that will give us our power losses. which would be great if we had our IRMS. So what is IRMS? Well, that is just going to be our square root of our period averaged integral 0 to t of our current. So our IL of t dt. Um, great. For this, not too hard to calculate by yourself, but I basically just watched a video of a guy doing this exact thing, and he came up with this equation. Great video, by the way. If you want to learn a lot more about this kind of thing for 30 minutes, Tim McRae. But he comes up with this. So when you solve this integral, you get IL squared times 1 plus 1/3 delta IL over IL squared times our ESR. He's calling it ESR, which is, again, our DCR. He shows up here as well. So that's great. We have that, which I just punched in here. The only thing that I've done is I've said, well, what is our delta IL over IL? So let's just go to a different section here. Our delta IL over IL. This is just going to be our percent change. So this is going to be like, 20% in our example, times our current. So our change in current, this is like our sort of magnitude. So our actual magnitude between the top and the bottom here. So it's our percent change times whatever our actual current is, divided by our actual current. And you can see these cancel. So this just becomes our IL ripple, is what I've actually called it in the sheet. So I'll skip writing that all out, and I'll just show you the sheet here. So if we remember, we've called this IL ripple, which is just our peak-to-peak percentage. And that's what I've thrown in here. So IN squared, so that's our IL, times that integral solved, which is just 1 plus 1/3 times our IL ripple squared times our DCR. So IL squared times our 1 plus 1/3 percent ripple squared times our ESR, which is our DCR. There we go. That's our sort of conduction losses, copper losses, DC losses, whatever you want to call it, in an inductor. And like I said, totally possible to calculate our AC losses. It's hard to approximate this. So I'll try and get some average values for this, maybe get some values based on a data sheet. But for now, let's just leave this blank and move on to our capacitor losses. So our capacitor losses are going to be essentially the same thing. We're going to work with the equivalent series resistance, same idea. And capacitor is going to be something like this with an equivalent series resistance. And we have current coming in and out. So we're kind of sloshing it through this resistor. And so in order to look at this, we have to look at the waveform. And a capacitor current is, again, going to be sort of that rising and falling thing. And we're going to do exactly the same thing. So we need IRMS squared times R. And I just found a video of a guy who calculated it out. Same guy, Tim McRae. Great. And he finds it to be the delta IL divided by square root 3. So our power losses are going to be the delta IC squared divided by 3 times our equivalent series resistance. And I put that in the sheet, and that is your capacitor losses. After that's all added up, looks like we're above 98% efficient. But again, I don't really trust these numbers super, super well. I want to add in some more losses over time. Hopefully we'll be able to fill this out to create a proper analysis. But for now, assume under this, so around 98% efficient, and we'll design our converter for that. In the next video, we'll be going over the component selection. So we'll try and choose a MOSFET, a diode, an inductor, and a capacitor, and a brief kind of introduction of how you would, power this and control it.